Morning. All right, so this week the lab will be about logistic regression, and so you do a bit of training on classification. Okay. So trying to finish your least square lab for before tomorrow. Okay, so today we'll be looking at some of the classic methods for machine learning, and in this course, we'll be starting looking at deep learning really from next week on. And so that'll be the most prevalent type of machine learning technique we'll be looking at. But you have to know that there is a lot more than deep learning into machine learning. And then there's this whole zoo of different classifiers and different techniques that have been established before by different communities. And if you go to an interview for a job, probably they will ask you questions about these other techniques, okay? So you better know that these techniques exist and they can do their job very well at the particular task, okay? So in particular, in the handouts here, we'll be looking at k-nearest neighbors, decision trees, support vector machines, and in particular, looking at the kernel trick, okay? There are different other techniques. These are they all belong to the type of machine learning we call supervised learning. So does somebody remember what supervised learning is? Can somebody tell me? Between unsupervised and supervised, what's the difference? Somebody? Yes, you know.
Supervised ones have the Y value, isn't it?
Yes, so supervised, you have the Y level. So what does it mean? So it means you have your observations, you have collected the features, but not only you have collected the features, you have collected what the outcome you're looking for, okay? So in the first example on least square we gave, we collected the height of the people, but as well their weight. So we could predict the weight from the height, okay? In unsupervised learning, something I'll try to have a quick lecture if we have time at some point. In unsupervised learning, we don't have access to the Y value, okay? So it's a bit more, here's a bunch of data, okay? You have a data set trying to do something with that. And so in unsupervised learning, you don't really have a clear definition of the problem at hand. What you're trying to do is to understand how the data is organized in the population, okay? So you're trying to learn more about the structure inside the data sets. Okay, so we're going to start with k nearest neighbors. And so k nearest neighbors is a rather simple one, and actually works well. So in this case, what we have is we have two classes. So the red cross, or magenta cross, is class 1. And in this example here, the round one is class 0, okay? And what you have here is a data set with, so I'll just zoom in a bit more. So you have a data set with 2 features collected. And so you have x1 and x2 here, okay? So the question you have is, in machine learning, is you want to make a prediction. So if you look at the black point here, you want to know, so that's in your test set or in your application, you want to know, what is the expected value, expected class for that particular point. And in k-nearest neighbors, very simple. So you look at the k-nearest neighbors in that feature set. And so in this case, we're looking at the distance between the feature vector of this guy and these guys, okay? So we're looking at really the Euclidean distance. So this would be a vector like this, so it would be x1, x2. And we'll be checking that we'll be checking at the Euclidean distance between this vector and all the other vectors we have in the data sets. And then basically count the number. So we stop this exercise at k, so that's why it's called k nearest neighbors. So we find the k nearest vectors, and we basically take the proportion, we look at the proportions of outcomes we have. So in a 3 nearest neighbors, this is the radius we're looking at. We have these 3 points, and we have 2 of class 1 and 1 of class 0. So you'd say the outcome, you would be class, so in that range, so in 3 nearest neighbor, you'll be the probability that the outcome is 1 given your input is 2/3. Okay? Just because you count, you have 2 of class 1 and 1 of class 2. So if you look at a 5 nearest neighbor structure, so we have now 3 blue, 3 class 0 and 2 class of class 1. So the probability this time that the outcome is 1 will only be 2 out of 5. Okay? So that's a rather simple algorithm that you can implement in any language in a rather short amount of time. So very simple to implement and makes a lot of sense, okay? The problem, of course, so I'm going to show you this. Yeah. Yes.
Why does it make a lot of sense?
But it makes a lot of sense because you start from the training set and you want to know if you have similar features, you expect similar outcome, right? And that's the same thing for every single method. Your starting point is to say your labeling function is a function of your feature, and therefore you expect that if the features are very much similar, then the outcome should be similar. All right, so let's look at some of these graphs here, okay? And these graphs I'll be using throughout this handout. So on the left, what you have is 3 different problems, okay? And so you don't have crosses, so, but basically you have 2 colors here. So red is class 1 and blue is class 0. And so for each of the problems, so this is the point cloud, again, looking at 2 features only. This is a point cloud for problem 1, problem 2, and problem 3. So here you see there's some kind of a boundary that goes like this. In problem 2, you have a boundary that is kind of circular. And here it's more a linear separation, okay? Now, I know this is the case because this is how they were generated, okay? So these are generated data sets. So I know that this is actually the real shape of the separation I have between the 2 classes. So on the first column, you have the result of the 1 nearest neighbor. So 1 nearest neighbor means you, given a feature vector, you're going to look in your training set, and you'll be looking at the one with the the closest feature in terms of Euclidean distance, and then the outcome will be the result of the outcome you had for that nearest neighbor in the training set. So the points of the data set are still overlaid, and it's quite faint, but it'll be visible on the PDF on the handouts. So the blue dots are still correspond to the class 0 of your training set in the data set. So it's just kind of overlaid. And what you see here is kind of the background now is colored either in blue and in red. And that means that for every single pixel, if you want, every single point in that grid, I evaluated where was the nearest neighbor. And based on that information, I looked at so I predicted the outcome. And so what you see here is the prediction of the outcome for every single point in that 2D space. Okay, so say that again. So if I take a point at random here, I looked at what the value x1 and x2 were, and I used a training set to find what the nearest neighbor was. So in this case, probably this point here, and I've assigned the label blue to that particular point on the image. Okay. Yes.
For this algorithm, is there any way of telling what neighbors maybe to start with, or do you have to go calculate the distance for every single point in the data set and go from there?
Yes. So this is a big problem. Okay. So you actually have, in theory, to look at every single point in your data set. So you have to compute the distance between the points you're considering, and you have to look at every single point in your training set to compute the distance, and then to get you back the value. Now, there is obviously it's very slow, okay? So there's been a lot of effort in the literature to try to find ways of organizing your data set in a way that you can do this kind of search faster. Okay, so finding nearest neighbors, there's like loads of literature on that. The main problem is there's no silver bullet. There's no way of getting exactly guarantee your nearest neighbor without actually looking at every single data point in your entry almost. Okay, so there is a technique called approximate nearest neighbors, and there's a whole range of stuff like we say, well, I guarantee that the k points I found you are quite close to the nearest neighbors. They're not the nearest neighbors. They're not guaranteed, but they'll be quite close to some error epsilon that you can formalize. But it's still quite intensive. Like whatever you do, it's still quite an intensive process. So in the second column here, what you see here is the result of the 3 nearest neighbors. And you can see now you have different shades appearing. And that's because I'm taking the proportion of points in the neighborhood that are, belong to one class or the other. So the shade corresponds here, if you want, to the probability and to likelihood. So the deepest intensity of the shade means you have 100% certain that the outcome is 0 or 1. But if you have a lighter shade, then that means like maybe you have a proportion of 2/3 or 2/5 and so on. Okay. So you can see here that the boundaries start to, as you see at the edge of the class separation, you start to have a bit more unknown in the process. And as you go with more neighbors, you gain a bit of smoothness in the boundary. So here the boundary is quite abrupt. Okay, so you really follow. It's not a nice smooth line. It's really just following whatever the closest point is. Whereas when you have 10 nearest neighbors, you have a bit of a smoother boundary. Okay, so same applies for the other problems. Okay, any question on this representation here? It's quite clear what's going on. Okay, so remember the shade here corresponds actually went through the grid of pixels, if you want, and for each of the pixels, I evaluated what the prediction should be based on the nearest neighbors on that particular pixel. So, okay, so the pros of this technique, okay, so it's a non-parametric technique, and what that means is, in logistic regression, I had to estimate what the parameters were. So I had the W's, so the weights, and I had to find some kind of technique to optimize for that. Okay, and as you will see in the lab, well, it's not an instant technique, and you have a bit of a, remember you have the gradient descent, so it takes a bit of time to get to the convergence. In this case here, we don't even have that. I mean, there's no model to compute. You just evaluate straight from the training set. So that's very good. So you don't have any parameters. There's no training path. And if, all right, it's a big if. But if you have a very large training set, okay, then it will actually work quite well. Okay, so that would be actually quite good. The problem is usually the training set is not very good. And if you come back to this example here, if you have a point, say here, so the further away you are from your data set, okay, so if you extrapolate a lot, so if your test point is very far away from the rest of your training set, then the distance, you'll be looking at distance from this point to the nearest points in your training set, but because you don't have a lot of points in your training set, this distance is a bit arbitrary, okay? So when you're very far away from the training set, the way you assign your points is a bit arbitrary because it's a bit arbitrary that you assign, like these distances will be very far anyway, okay? So the less points you have in your training set, the more arbitrary the assignment is, okay? Just by the nature of the problem, because you have very few points and there's an element of randomness in the way you picked up the points, so the way you're going to assign this point, which is very far away, will be a bit random. So the quality will deteriorate quite a lot if you don't have a lot of points. The second point, this point you raised, is that it's actually quite costly to compute, okay? So if you have a training set with millions of points, then it becomes totally impractical, okay? And the last point here is you don't learn too much about the feature themselves. And something that will become apparent with neural nets is that what you want from machine learning as well is not only to predict, but it's to understand your problem a bit better, okay? With this technique, you don't understand your problem any better because you just look at your training set and you just know as much as your training set. So there's no, at least in a parametric model, you make some assumptions about the model, you have some kind of understanding or at least hypothesis about what the model is. Okay? Any questions on nearest neighbors? So very good. It's more like a hack. If you have to use it, it's more like think of it as a hack you want to use, okay? All right, so the next one, it's a whole family of problems that I call decision trees. Okay, and they were quite popular just a few years ago. So even like 5 years ago, you'd see people doing PhDs on that. And if you look at techniques, say, so you know the Kinect, right, for Microsoft. So the Kinect is this little sensor you have to play games, and they can sense, you know, the 3D geometry of the person in front of it. And in the Kinect, they have a system that can extract a skeleton from you. Okay, so you have a model. They kind of can build a model of you as a stick figure. And the way they've done that is using decision trees. Okay, so using random forest. So they use machine learning to be able to match what the camera sees to what really they think of the hand or the feet and so on, body parts. Okay, so to identify these body parts, they used random forest. Okay, so that was just a few years ago. Now, of course, they moved on to deep learning, but even the Kinect 2 was using random forest. So very, very popular technique. So the way decision trees work is that they can try to partition the training set into different regions. And the way they're going to partition that in a kind of recursive way is by taking simple decisions along the axis. Okay? So I've drawn here an example. So this is my training set. So again, the real class separation is somewhere here. Okay? But we express the classification algorithm as a tree of different little tests. And in this case, at the root of your tree, you have the first test, which is just to test whether the value of x1 of the first coordinate is bigger or smaller than 3, greater or smaller than 3. Okay? And that corresponds to that partition here. Okay? So we split the entire training set into two, and we say right, this will be the first decision I take, and depending on where you fall on one or the other side of that cut, then I will take a different set of questions. Okay. And so if you are less than 3, then you're going to look at the second decision, which is to test whether the second, in this case, the second value x2 is less than 2. Okay, so that would be this test here. Okay, and basically at this point you have only 2 possible quadrants. So either you're here or either you're here. Okay, so this is at 2 parts of the space you're looking at, and well, actually that would be bigger. That would be the entirety of this space here or the entirety of this space here. All right, and in this case, if you're less than 2, you're here. So that means that you're class 1, and if you're in that part of the space, you're assigned to class 0. All right, here I'm not explaining how we get that tree. Okay, so there's loads of different techniques how you can get that tree, but basically the way you evaluate your algorithm is based on this idea of having a tree of your data goes through this kind of a tree data flow. Okay, so you test at each node of your tree. You're going to make a little test, and the test is only based on one of the coordinates. You check one of the coordinates, and you check whether it's bigger or smaller than some value. Does it make sense? All right. So this is a very classic way, and as I said, I'm not explaining how we get these trees, but usually it's quite fast techniques. Okay, the training is quite efficient. So I'll show you some examples here. So working on the same training set. So here on the left, you have the 3 problems and 3 different boundaries, which I will show again here. The first column here, well, there's 3 types of algorithm, and they're all decision trees, really. In the first one is just one tree. So that's why it's just 2 shades of your algorithm, of your 2 shades of blue and, sorry, either you're 100% certain in each case, okay? At least that's what the algorithm says. So there's no notion of probabilistic, like you're not trying to average results at this point. Okay, and you can see the boundaries really kind of split that into a kind of checkerboard pattern almost. Okay, so you have these regular vertical or horizontal structures in your decision. Okay, and that's just how you took all these decisions. In the 2 other ones, so random forest and AdaBoost, what is done here is that you take multiple trees. Okay, so you construct multiple trees, and you look at the results. You're trying to evaluate every single point by evaluating multiple trees, and you take these trees might not agree on what the outcome should be, and you take the average. Again, as in nearest neighbors, you take the average of these trees, and that's how we have a more kind of a probabilistic view on that. Okay, so random forest and AdaBoost, multiple trees that aggregate if you want your decision. Okay, so the problem you have is kind of coming back. So the pros, okay, there's lots of pros. Okay, and just put 1. It's fast, and the second thing is as well is it's very easy to explain to a decision maker how you derive the outcome. Okay, so let's say you're working with a medical application. People might want to understand how you come up with a decision of somebody having, say, a brain cancer or something like that. So in decision trees, you can very simply look at the path of your decision in your trees and realize why this particular decision was made. You can come to a policymaker and say, I took the decision, or that self-driving car turned left instead of right because of that decision. Okay, so that's very, it's a very nice property. that is a very nice property in theory, because obviously modern random forests and trees have potentially hundreds of thousands of nodes, and so when you have loads of nodes in your tree, things become a bit complex. The second point is that it's fast, and that's a good thing. So if you have an embedded platform, such as the Kinect, that makes sense. You can do that very efficiently, and you don't use too much power. The problem you have with random trees, decision trees, is the following: that most of the decisions, as you've seen, are taken. I mean, they're all taken along axes, okay? And so you have this kind of, this vertical and horizontal pattern here. But in our data set here, the decision really should have been along this axis. And that you cannot do with a decision tree, okay? Decision tree will only look at each axis individually. So the best a decision tree would be some kind of staircase here, okay? And that will, you will need a lot more, like your decision tree will be horribly inefficient on that particular instance. So you kind of have it's not, the performance of your decision tree depends somehow on the way the data is set up. And if you rotate your data, then you will be much more inefficient. So you have, it's not a nice property to have, okay? All right, so that's for decision trees. So I put links on the handouts to some YouTube video you can check on that, and to some other references for all the other ones. All right, so come support vector machines, okay? And this was the most popular technique just before neural nets, okay? So people would use random forest if you were looking for speed. So just before deep neural nets, so just before still around 2012, people would use, if you want accuracy, they would look for support vector machines. And if they were looking for speed, they would be looking for decision trees. So the thing to keep in mind for you is that support vector machine is no different from logistic regression, okay? So you still start from a linear classifier model, okay? So remember, this is your score, and this is just the outcome. You checked whether the score is bigger than 0 or not, and if it's bigger than 0, you say the class is 1, and if it's not, it's 0, okay? The only difference you will see is the loss function itself. So in logistic regression, we made the assumption that the noise component was following the logistic distribution, and we used the cross entropy, okay? In support vector machines, we use a slightly different loss function, which kind of looks like this, and I won't get into the details of that, but basically, just keep in mind, it's a different loss function, okay? So we're minimizing, we have the same model, we're still trying to split the model is exactly the same, okay? We still have that, okay? But the way we're going to solve for that is slightly different and leads to a slightly different equation, okay? So there's some kind of a geometric interpretation to that. And again, I won't go into much detail. There's way more maths behind that, especially in the optimization, how you find it. But the idea here is that, so if you have your two classes, you still be looking for a hyperplane or something, a surface that will separate both classes. And the direction we'll take will be the one that maximizes the distance between the two classes. Okay, so you might have a gap between the two classes, and you're trying to find a direction where the gap will be maximum. To give you an example of a direction that doesn't maximize the gap, if I take this direction here, there's only that much of a difference between the first point here and the first point here. Okay? So the distance here between the class 1 and the class 0 is smaller than the distance between these classes. Okay? So in the SVM, you're trying to find a direction where there's an obvious difference. So when you're going to compute the score, there will be an obvious difference, the most obvious difference possible between class 0 and class 1. Okay, so you're trying to separate the two classes as much as possible. Yes?
A question for you. Why did you draw a line like that? Because if I draw a straight line across the two, why are you drawing the line perpendicular to the other?
The D.
Explain it, right? You talk about distance between the 2 points closest to the line, right?
Yes.
But what do you mean by closest?
What do you mean by closest?
Perpendicular, right?
Perpendicular, yeah. So these points here are the one that will touch the line, and this one here be the one touching this line. And here we're looking at the maximum difference between these two virtual lines, if you want. That corresponds to the margin you have in between. That's kind of the no man's land, if you want, between the two classes. So you're trying to have a no man's land between the two classes, and you're trying to find one direction that will maximize the no man's land. I invite you to look outside of this. Yes?
Can you explain what you mean by hyperplane?
Aha. All right, so this is something from linear algebra. But basically, here in your space, so you're in 2D, okay? The separation between my two classes is just a straight line. But if I were to be in 3D, the separation between my two classes would be a plane, a 2D plane. If I were to be in 4D, it would be a cube, a volume, a 3D volume, and so on. So we don't want to think too much in ND, but basically the hyperplane, if you have a space of, if you're in a space of dimension n, the hyperplane will be of dimension n minus 1. Okay, and I will separate. That's a space, if you want, that is orthogonal to a line. If you take a line is still a line in any dimension. If you take the space which is orthogonal to that line, that space will increase in dimension every time you increase in dimension. It's not super trivial to visualize. Just think, if you're in 3D, that this separation will be a plane. Okay, and don't think 4D because that will blow your mind. But just think, okay, here it's a line, but in 2D there will be a plane. What you're really looking at is the key element. Okay, why does hyperplane comes in place? This is because really what you're looking at is this direction. Okay, and this direction is a line. Okay, so when you do X transpose W, this is a score, okay? And this is really what the direction you're taking. So remember the example I gave of the washing machine, okay? You're trying to buy your washing machine, and somehow you need to compare all these things, all the features you have, okay, about the washing machine. You need to collapse that into one single value. And this is what you do in all the linear models. You collapse everything onto basically what is a line, okay? And that line, if you're on the score line, is what will give you the value of the score of that X transpose W. So in that case here, you have this line here, which says that X transpose W here is much less than 0. Here, X transpose W is much less than 0, much more than 0. And in the middle here, you have X transpose W, which is null, okay? So the space where X transpose W is null is, in this case, just a line. But if you were to be in 3D, that would be a plane. Okay, so that equation would correspond to the equation of a plane. And if you were to be in dimension n. That would be a space of dimension n minus 1. Okay, all that is a bit kind of maybe hard to grasp if you've forgotten about linear algebra. But I think what we're trying to do always is to, that's what I said for logistic regression. Okay, you have two parts in your problem. The first part, and that will come true for deep learning. The first part is to collapse, like x, the features you have is p-dimensional in our case, okay? So this is a high dimensional space potentially. And we don't want to work in that high dimensional space. What you want to work is with scalars, okay? So the first thing you do is to compress that dimension into, to do a dimension reduction to go from that high dimensional space to this just one value. And then once you have this one value, you can apply a threshold. So that's the second part. So you apply a threshold, which is a nonlinear operation that allows you to take a decision based on that single value. Okay, so two steps. First, you reduce the complexity of your problem by reducing the dimensionality, and then you take a simple threshold operation. Okay, so all right, there's a lot more to SVM, okay, and especially the way you trying to solve for it, and I suppose geometric consideration about what it does, okay? The thing is, you'd be tempted to think that, okay, so is logistic regression any worse than SVM? I mean, everybody has been talking about SVM, so it has to be better. And the answer is no, okay? So there's no practical difference for you between logistic regression and SVM. Really, in terms of performance, I wouldn't know, studying a problem, which one is best, okay? And something to keep in mind is this no fringe theorem. It kind of echoes what I said before about the fact what really we're doing is like, in this case, we're using different loss function, okay? And remember what I said about the loss function and the relationship between the loss function and your data, okay? Your loss function is really kind of prior information you have about your problem, and you're trying to, or about your error in particular. If you have different prior information, you should use a different loss function, a different expression for it. The no free-lunch theorem kind of formalizes some of these elements and basically says, if you have, so on the x-axis here, you have a whole range of possible problems you might have, plenty of data sets. And on the y-axis here, you have the performance. And each classifier will behave differently over the range of all these problems, okay? But really what it means is that for the problem you have at hand, maybe you want to use classifier A. Okay, that would be very good. But classifier A will have to be not as good on other problems, okay? So the average performance over all problems, possible problems, is the same for all classifiers, all right? This is just keep that in mind, okay? So when somebody says, you know, I think SVM is better than this, or this classifier is better than X, and so on, it's all relative to the problems at hand, okay? And so it might be that in your case, with the kind of problems you're looking at, SVM is better than logistic regression. That's possible. And it might be that for your entire life, you prefer to use SVM than logistic regression because systematically the problem you're looking at are more suited for a hinge loss function than the cross entropy. All right? But just keep in mind that it is not necessarily true all the time. You don't have a silver bullet. You don't have a classifier that will work better all the time. Okay? It's all about, you can't do machine learning if you don't use prior information. You have to give educated guesses. You have to make assumptions about what your data looks like. You need to say, I know this problem is of this shape. I have some ideas about what the error function should look like. So therefore, I'm going to use one of these classifiers that best suits this intuition. Okay? This is a bit vague for you, but this is just kind of a reminder. If somebody tells you, oh, this technique is much better than these other techniques, it's all relative on your problem. Okay, it's probably true, but it just means that for the class of problem you have, that is true, but if you have a different class of problem, that would be different. Okay? And similarly, don't try to extract too much from that. Okay, this is more kind of a reminder. Don't try to use that as a gospel. That like this is based on. You have to read the paper to really understand what the implication of that really is. Okay, so the one I'm giving you, the implication is the one you should keep in mind, which is just don't try to say that classifier A is always better than classifier B and C. Okay, in theory, they all have their strengths. Okay, so I'm just going to finish with that part, and I'm going to upload a video explaining the kernel trick, because I possibly don't have the time to explain the kernel trick in such a little amount of time, and I suppose it's not the point of the lecture, but I'm still going to have upload a little video explaining that, so try to look at it before the next course. So remember we've done, okay, so this is a very important point. Linear SVM, not that interesting, okay? So same with logistic regression by itself, it's interesting, but still you assume that the class separation, the way you separate both classes, it's a straight line. And that is a bit limiting, okay? So remember what we've done with least square is we're trying to say, even so we only had one element, which was x, we could somehow come up with an augmented feature, call it phi of x here, which is here a polynomial expansion of x. And I could do that because, remember, least square is linear in the model parameters, okay? But not in the features. So the features can be whatever you want. So I can do that, okay? This is something I can do, and that's very nice. And that was the idea, okay? The idea was to say, on the left is my real problem as I collected it. So these are the features I collected, and the class separation here is a bit hard, okay? So it's not a straight line. But somehow, if I find the right set, so maybe not a polynomial, but maybe cosine, list of cosines and sines, or maybe any kind of other function I can come up with, then somehow I will warp that space and map each of these points to a new location in such a way that now the separation between the two classes is just a simple linear problem, okay? So that's kind of what you want to do, okay? You want to work on your input features in such a way that after you transform your input features, the class separation will be, or your problem in general will be very easy, okay? So that was true for least square, it's true for classification. That's the thing you want to have. Now, you have two problems with that. So first, well, you need to find what this class expansion should be for all your problems, okay? So we found one, we looked at polynomial expansion. I tell you right there, it's not a good one, okay? It's probably the worst one you can think of. And so you need to find a generic way of finding phi, okay? Not obvious. The other problem is that this feature expansion means your problem becomes becomes much worse, okay? So I show you the expansion at dimension 1, okay? But here's, what if you have 3 features, okay? So not a big problem, you have 3 features you collect. If you do an expansion at order 2, you have, what is it, like 10 values now, okay? All right, so your feature vectors go from 3 to 10. Still doable, it's not the end of the world, it's fine. But the exact formula, if you have p features and you want a polynomial of degree d, that would be p plus d factorial over p factorial d factorial, which there's a lot of factorials here and doesn't look nice. And indeed, it is not nice, because if you collect 100 features, so nothing mad again, like if you're a bank, you know, 100 features, you get them. And if you're looking at a polynomial of order 5, which is again not much, then you have a feature vector of 100 million, okay, or 90 something million, okay? So 100 million features in a feature vector for just one customer, that's a bit much, okay? Especially if you think that you have to use least square, at some point you're going to have a matrix here which will be 100 million by 100 million, and that's not nice, okay? So these two problems, you don't know what phi should be, and even if you know what it is, probably the expansion will be mad, okay? So the solution to that is the kernel trick, and this is something you will find, I'll explain to you in this video, it's in the slides, I'll come across that, but the gist of it is all of a sudden you have phi which is implicit, okay? So you don't, they come up with a way of saying that you don't need to explicitly define what phi is. We're going to express phi in an implicit way such you never have to write 100 million, feature vector of 100 million, okay? So look at that for Wednesday, okay?